I want to explain one more thing about this stratified guys. One example which is actually quite nice. So let's take an algebra together with an augmentation. Well, let's just stick to the k-linear setting. Okay. So now we have a so we can view k now as a right module for x, let's say over a, and so we have this. So let me just draw a picture. So we have a here then k acted on by a through the augmentation map, and if I take the center of that, what I get, I have the center of A, which is, let's say, Orchil cochains. And now here I have, on that line, I have an algebra, which is R hom from K to K within right A modules, which you might want to write A fric, I don't know. And there is something really nice from so because Z of A acts as an E2 algebra on E1 here, it actually centralizes this algebra, which is A shrik here. So just by the universal property of the center of A shrik, we are going to have a map of E2 algebra from Z of A to Z of A shrik, which is just for free. And well, as you can guess, if A has some kind of cosine property, then this will be just equivalent to having this map to be a weak equivalence. Okay, that was just a remark. So I'll just use it later. That's why I wanted to make it now. And of course, what you have is really a factorization algebra on this corner, which is locally constant with respect to a depth 2 stratification, when you have those two pieces of those two strata of codimension 1 and then this one of codimension 2 here. So it's constant, it's locally constant here on those two guys and then on that guy here. Okay, so well, in general we have in general you can write there's a kind of broad generalization of Swiss cheese opera, which is I will just give the name. So there's a topological opera ENM, and let me just say that Swiss cheese is just the situation when you have, so usual little disk opera or EN0. Swiss cheese is E11. This one is E02. And in general, let me say that there's a statement which says that ENM algebras, so that this category is just equivalent to the one of fact Rn cross R plus M algebras, which are locally constant. Okay? And here the stratification just comes from the fact that each copy of R plus is stratified just by the boundary stratification, and it gives you a depth, probably M stratification. Okay, now let me just try to say a few things now about formality theorems. And maybe one first theorem is that if you take chains over this topological operad ENM, so I'm not writing, but it has, for example, for E02, it will have 4 colors. This one, this one, this one, and the corner. And I think you can guess the operations. So you might have configurations of guys here, configurations of guys here, and also configurations here. Okay? So this is a topological operad, and this one, if you take chains, real value chains on E and M, it is formal as a DG operad. And okay, so the proof is, I mean, I'm not going to write the proof, but let me just say a few words. So the proof goes in many steps. So first step is you have to prove that this E and M is actually equivalent to some C and M bar, where C and M bar is an operad of, so you take configurations of points on this space here, and then you compactify it in a suitable way, and it basically gives an equivalent operad. So that's the first step you make. Second step, I mean, all what I'm going to do is just copying Kontsevich proof in the case m equals 0. It works just almost the same. The second step is, well, then since those two are equivalent, then this one is equivalent to chains on the second one. And then you have to say, okay, I'm just taking chains over now this configuration space operad. And within this, I'm just going to consider only so-called semi-algebraic chains, so chains which are given by algebraic inequalities. Third step is to write a morphism of operad between that guy and an operad of graphs. So this I'm definitely not going to explain. Just I want to say that it's very similar to the proof of Kontsevich formality theorem.
Which kind of graphs are you using?
Okay, so right.
Which variant of the graph?
So okay, so you have to have graphs with many labels, because you will have vertices for, so you will have as many kinds of vertices as you have stratas in your configuration space. So in the case when m equals 0, there is only one kind of vertices, and then you have to, actually you can get rid of any condition on your graph, just because then the map you're going to write, integrals, and the graph you don't like, they will just have a weight 0, so that does not matter really. Okay, how could I? I really don't want to go into this actually. Maybe we can discuss this later if you want. So basically, well, let's say in the case n equals 1 and m equals 1 also, you exactly have the graph which appear in Kontsevich formality theorem. Basically, so you will have two kinds of vertices, one in the vertices in the upper half plane and vertices in the downstairs, and you will have just things like this. You might have this. Basically, you really don't want arrows to go upwards, so the arrows should just only go in one direction in the stratification. They should never go back. There are a few restrictions you have to put on this. And basically, the map you have here is constructing appropriate differential forms on this configuration space, and then to any graph, you associate one specific form which you're going to integrate on chains. I mean, I don't want to go too much. And then the last step is to prove that this guy is formal. So this guy is quasi-isomorphic to its cohomology. Okay. I want to talk about application of this, actually. So, So the first application is some kind of higher dimensional version of Concevic formality theorem. So you just start from the following commutative algebra. So just take a free commutative algebra generated by a finite dimensional vector space. And look at it. So it's a commutative algebra, so you can look at it as an EN algebra. And you're just going to take its EN Orchil cohomology, or EN Orchil cochain complex. So let's take just H EN of A. So which is nothing but the centralizer of the identity of A, so namely center of A within EN algebras, or within locally constant factorization algebra on Rn, if you wish. So we know that this guy is an En plus 1 algebra. And we know that its cohomology, so the cohomology of Z of ENA is actually S of V plus V dual shifted by N. And you see that it has a Poisson bracket of degree, I guess, minus N. So it's what is called a Pn plus 1 algebra. And Pn plus 1 for me is just the homology of En plus 1. So it means that it's a commutative algebra together with a Poisson bracket of degree, in this case minus N. And what I would like is that definitely I cannot compare those two guys. These are different algebras. I mean, different kind of algebras. But what you could say first is, well, if I have an En plus 1 algebra, then I have a Lie bracket of degree minus N. And the same if I have a Pn plus 1 algebra. Well, when I say a Lie bracket, I mean I have a homotopy Lie shifted by minus N algebra. And the same here. And you could ask if there is an L infinity quasi-isomorphism between those two. And there is indeed. And the way one can prove this is, I mean, it basically follows Tamarkin proof of Concevic formality theorem. So let me just sketch how it works. So first of all, you're going to use, okay, so let me write those guys. So use the formality of chains En plus 1 R. So we are in the K-linear setting, so we can just act by chains. Well, with value. So I would have to assume that K contains the real numbers. To get a homotopy Pn plus 1 algebra structure on Zen of A. So that's the first step. We use the formality theorem. Then we know that those two guys are definitely quasi-isomorphic, just as cochain complexes. Okay? Because, I mean, in cochain complexes, everybody is formal. So then we can use transfer of structure. To get another, well, homotopy Pn plus 1 algebra structure on SV plus V dual shifted by n, which is such that this guy and ZENA are Pn plus 1 quasi-iso. But the point is that the Pn plus 1 structure we get here is not necessarily the one we had right from the beginning by just taking cohomology of something. Actually, it's a deformation of that one. And then the last step is to prove that there are no deformation of this of the Pn plus 1 algebra structure you have here. So the last step is Z of V plus V dual shifted by n is rigid as Pn plus 1 algebra. And the way you prove this, you do it in two steps. You have to use some spectral sequence. So first you prove that it's not deformable as a commutative algebra just because it's a free algebra. And then you try to compute Poisson cohomology of that guy, but that guy is symplectic. So Poisson cohomology just coincides with some shifted Durham cohomology, and we are just on vector space. So Durham cohomology boils down to just nothing. And that's a very, very sketchy, it's not a proof. It's just a kind of just summarizing steps of the proof. And that's how you prove that this guy is rigid as a Pn plus 1 algebra. So the homotopy Pn plus 1 structure you get here is actually just equivalent to the strict one you had in the very beginning. Okay? Actually, you can, so this can be improved into a formality for pairs ZENA, A on one side, and S of V plus V dual shifted by N, and SV on the other side. So here you have an EN1 algebra structure. Here you have what I will call a PN1, which is just a Pn plus 1 algebra acting on a Pn algebra. And okay, so what you just do exactly the same thing. You use formality of this to get a Pn1 homotopy structure, then you transfer, and you have to prove that this situation here is rigid. But it's not true that this pair here is rigid as a Pn1 algebra. It's rigid as a Pn1 algebra such that this one remains fixed. And that works just in the very same way. In the end, it boils down to computing some Poisson cohomology of symplectic guy. Right. Okay. Maybe the last thing I'm going to explain is.
So, yeah. Usually with EN algebra, sometimes it's enough to prove in the case n odd or n even because it's spirit of dimension. So, is it true in your context? As soon as you have proved that for n odd?
There should be. I don't know. There is something like this. When you write this graph complex, basically the graph complex for on all n odd, they look very much the same. They have the same sign rule, and basically if you go from n odd to n even, basically the sign rule you have on vertices is usually opposite to the one you have on edges, and the role is reversed when you go from n odd to n even. But I don't know a proof that really says just okay, it's sufficient to do it for E2 and you get it for all E even, and for E3 and get it for E odd, because still there are those integral and configuration spaces, and I don't know how to. I don't know how to deduce the case n even in general from just n equal 2. But that's definitely true that there are some similarities between the, all the even case look very much the same, and all the odd case look also very much the same.
Maybe can you motivate why you want this formality theorem for consideration? It's for the quantization of the Poisson.
That's kind of similar. You might just want to quantize shifted Poisson structures. So okay, those things appear quite often in mathematical physics. So if you have okay, I can just make one comment, which will be very imprecise, but there is this so-called AKSZ construction, which was improved by Ponteefter and Vacchi and Bezzosi, and it consists in the following data. So if you have some x, let me be very imprecise here. So if you have some x which is compact, it might be a weird space. But if it has some compactness property and some orientation, that's enough for us. And you just look at mapping space from x to y. So x is somehow compact and oriented. And assume that y has some symplectic structure. Or even, it might have some shift in this symplectic structure. Let me not say anything about this for the moment. And you have the evaluation map, which goes to y. And what people used to do in physics a lot was just take the symplectic form you have here, pull it back by the evaluation map, and then you would like to define some symplectic structure on the mapping space. And the way you do this is you integrate along x. And because you have something which is compact, oriented means that you have some fundamental class. That's allowed. I mean, you have to work to make sense of this, but still. And then you get, but then it will shift in cohomological degree your symplectic form by the dimension of x. So there are many problems so for example, you might want even to quantize an honest symplectic structure. And it might be easier just to kind of do some stuff like this, get a shifted one, quantize the shifted one, and try to go back. That's basically what Kevin Costello is doing with his BD algebras. That's one reason to be interested in this quantization of shifted Poisson structures. Also, in this quantum field theory, this mapping space appear everywhere, and they sometimes just carry natural shifted symplectic structure. And if you want to try to make sense of what quantization means, one way to make sense of it is just to produce some EN algebra. Well, I should say that producing an EN algebra is not so interesting. One should just deform the category of modules rather than the algebra itself. But okay. Maybe one last thing, and I'll stop. Okay, let's just consider this situation here, where we have A. So let me just draw this picture again. So we have S of B here, then wedge of V star here. So this is a Kosul type situation. And then we have K here. And I would like to have a kind of formality theorem for that. Meaning the following. I know that I have formality theorems for those two guys. So I know that if I have a Poisson structure here, I can quantize it. And any Poisson structure here gives me an infinitesimal deformation of that guy here also. And I can also quantize it. So namely integrate it to a formal deformation and not only a first order one. The main problem is I would like that when I do this, I can deform in a compatible way the whole picture together. So not only deforming SV and wedge V independently, but in a way that they remain cosine dual to each other. So that's actually something. So together with Giovanni Felder, Andrea Ferrario, and Carlo Rossi, we proved that one can quantize in a way that preserves the cosineless property. This is a rather imprecise statement. So one way to prove this is the following. So I'm not going to repeat all the steps we had, but again, you have to use the formality of E02 now. But the idea is you have the following. So you have S of V plus V dual shifted by 1, which is both the Orchil cohomology of SV and wedge V dual. Okay? And we know that we have, okay, if I want the algebra structures, I have probably to shift back by -1 here, I guess. Here I have center E1 of SV, shifted back by 1 to get an actually, the algebra structure. And I have Z E1 S of V dual shifted by 1, which is wedge V dual. So here I have L infinity algebra. So I have Lie algebras, and they are all. I have isomorphism in the homotopy category of DG Lie algebras between those things, and I also know that those two ones are just equivalent as even. If I don't have the shift, they are equivalent as E2 algebras. So in particular, they are equivalent as Lie algebra here. But I have absolutely no idea a priori if this diagram is homotopy commutative. I just know that there are basically weak equivalents there and there, but I don't know if this diagram is homotopy commutative. And basically, you can use the formality of E02 to prove that this diagram is homotopy commutative. And what it tells you is that whenever you give yourself an infinitesimal deformation either of SV or wedge V dual, which are just the same, you can integrate them or quantize them into actual formal deformations, and you know that those formal deformations will be cosine dual to each other up to some up to one thing I'm going to just tell you now, is that contrary to what many people say, this guy is not the deformation complex for E1 algebras. So it means that when we do quantization, we do not always get quantization. So if you have a Mohr-Cartan element in this Lie algebra here, you get an actual infinitesimal deformation of SV. When you go here by this equivalence, then you get a Mohr-Cartan element here. So let's just realize our homotopy algebra just as A infinity algebras. So then you get an A infinity deformation of SV. Fair enough, SV is concentrated in degree 0, so there is no problem here. But on that side, now this guy is not concentrated in degree 0. You might have A infinity deformation, which are so-called curved, which are not actual deformation in the homotopy category of algebras. This comes from the fact that there's a fiber sequence. So you have the deformation complex of A. It goes to Z E1 of A, and then you have A here. There might be some shifts. I guess this is one here. We have a fiber sequence of Lie algebras. So the right guy is the deformation complex. So a more carton element in this Lie algebra, I guess I should, actually everyone is shifted by -1 here, and this one is not shifted. So this one is a Lie algebra, and more carton element here are actual deformations of A within the category of the homotopy category of Lie algebras. But elements here are not. If they don't go to 0 here, they might not come from a guy there. So the actual statement, when we say that one can quantize in a way that preserves costliness property, it should be phrased in the following way. So we have deformation here, and as soon as the deformation we get are not fake deformation, namely that they all come from element here, then they are cosilial to each other. But if one of them is curved or fake, then, I mean, even the statement does not make sense. Okay? I think it's time to stop.
Thank you. We have time for questions. Any question? You prove this. The proof you have of this higher formality follows this marking, so you keep the obstructions and blah blah blah. There are other proofs.
I guess you can mimic Kontsevich proof, and it should
I had more or less
work perfectly the same.
I had more or less Tolbuchev-Tsigan. We need to rectify and blah blah. So
I must say that I've never read really seriously what they did, so
that's wrong.
No, I mean, for example, I could just improvise some proof of Tamarkin or Kontsevich, but I could not improvise on what they did. I don't have in mind the main steps, let's say. So I cannot say how they could generalize to this higher formality.
They even use the fact that Gerstenhaber is a causul operad, and they have bar-co-bar pointers, and they rectify the algebra, and that's how they build explicitly.
Yeah. So what scares me a bit is that I think they use this operad of natural operations on the Orchil complex.
I'm not sure that in that paper they already use.
I mean, they use the form of the Deligne conjecture, which goes from use those B infinity algebras or whatever. I don't know the higher version of that. So what I did is kind of using the same strategy as Tamarkin, but using a different form of the Deligne conjecture. So I actually don't know what is the operad, the kind of the analog of the B infinity operad for this higher stuff. So, and that's actually a problem for this thing. I mean, there is no kind of nice algebraic model for En. I mean, for the action of En on the center.
You mean the equivalent? You mean the analog of B infinity? B infinity.
Yeah, the
braces. You put the cup and.
Yeah, exactly. That's what I mean.
Okay.
I mean, when I say there is no, I don't know any.
Yes, yes. Never make such a claim. Any question? Thank you.